CSE 571, Probability Basics, Lecture 2. Hi, today we are going to continue with the independence random variables, and we're going to see how we can calculate the conditional probability of random variables. Let's say x, choosing random variable x. Hi, today we're going to continue with the random variables. What is the concept of independent random variables? Let's say we have two different Hi, today we're going to continue with the definitions of probabilities. Let's think about independent random variables. If we have two different phenomena that one neither makes the other one more or less probable, we call these two phenomena independent of each other. This is how we write them. Assume that we have phenomenon of x becomes a specific value and the different probability of phenomenon of y become a different probability will be calculated as the multiplication of those two phenomena together. For instance, no matter how many heads you get during a coin toss, it doesn't affect the outcome of your friends getting heads or tails, and vice versa. Let's think about conditional independence along this same definition. If we can say that phenomenon z is independent conditionally from x and y, if and only if that knowing z does not add or delete any additional information from y. And this is how we write it. Given that probability of x equals x and y equals y, given z, we can say that the probability of this event given z will be multiplied to probability of y given z. Let's see an example. Let's say that you're testing for a rare disease in a clinic, and the probability of you having the disease in a Let's make an example. Suppose that you test for a rare disease, which the probability is 1 in 1,000 that you have the disease in the population. And the result of the test is positive. With what probability we can actually conclude that you have the disease? Let's put it in the format of conditional probability. The probability of you having the disease, given that you tested positive for the disease, is pH given E. And the probability of you tested positive, given that you have the disease, is PE given H. And the probability that you have the disease is pH. And we have to divide that over the probability of the success rate of the disease. Let's put some numbers. For instance, let's say the probability that the test is positive given that you have the disease is 0.99%, is 99% or 0.99. And as we mentioned, the probability of you having the disease is 0.001. So we have to divide that over the probability of E, which is the probability of having the disease times the probability of the test is positive given that you have the disease times the probability of you don't have the disease given that the probability that this is a false positive. So put the numbers there. We have, this is a plus. .0%, which is, if we calculate the numbers, it is 9%. So it means that if we go to the first place and they tell us that we have the disease, only 9% we are sure that we have the disease. Let's think about a different case. What if you go to the second clinic and the result of the test is also positive? What is in this case? What now? So the formulation is the same, but the difference is the probability of V having the disease right now changed to 0.09 or 9%. So that changes the probability of the evidence. And when we put the numbers in, now the probability of us having the disease is 90.7%, which is a high probability and considerable. Now let's think about continuous cases when we have random variables in a continuous environment. Instead of probability mass function, we have to define probability density function, which is a function that describes the probability density in terms of an input variable x. Needless to say, that probability should be bigger or greater than or equal to 0 at all times, because we cannot have negative probability. And to find out the probability in the whole space, we have to take the integral. For instance, if I want to find the probability of this function between 0 and 1, I have to take the integral between 0 and 1. Actual probability can be obtained by taking the integral of the PDF. Now let's think about a cumulative distribution function, which is when we want to find out the probability of some event is smaller than a threshold. So here we're not trying to find out the probability of an event being a specific value. We're trying to find, comparing to the case that we're trying to find out the probability to be a specific value, we're trying to find out the probability that is smaller than a value. So to calculate this function, we have to sum over all the possible sequences, all possible phenomenons in the state space X, the sample space X, for discrete values. And for continuous, we have to take the integral. Now that we have talked about different definitions such as random variables in continuous space and cumulative distribution function, let's look at common distributions along the line. The distribution that we're going to talk about is normal distribution, which is used when we don't know the variable distribution of the random variable. For instance, we don't know the distribution of the height of the entire population. Therefore, we choose the normal distribution, which is a normal case for distributing all different phenomena in the sample space. Let's also talk about some other definitions, such as mean. So mean is the expectation for all the variables in a state space, and we define it as E of x. Needless to say, the discrete random variables in the discrete space, we have to take the sum of all the phenomena and take it as a weighted sum. We have to multiply the weight of the variable toward the probability of that variable happening. And in the continuous space, we take the integral. The variance, which is the expectation squared of the deviation between the value and the expectation of the actual value and the expectation of the value. The variance is the squared expectation between the mean of all the phenomena and the actual value. In the discrete state space, to calculate the variance, we have to take the sum of the subtraction of all the values from the mean squared times the probability. Basically, it's the weighted the subtraction squared of the probabilities. And for continuous space, similarly, we take the integral. If we have two different phenomena sum up together, their expectation will be simply sum up separately. And if we multiply all of the values to a value a, which a is a value in the reality space, in the real space, then all of our mean will be multiplied to that value. And similarly, if we multiply all the values to the same value, if we multiply all the values in a sample space in a value, and we add them to a constant value, the addition doesn't change the variance, but the multiplication actually makes the new variance to have this square of the value that we already multiplied. Also, if we have two different sample space x and y, which are independent from each other, the variance of the summation would be simply to sum the variances separately. Today, we talked about independent random variables and conditional independence, and then we talked about continuous random variables for both conditional independence and cumulative distribution functions. Then we talked about mean, variance, and the properties for both continuous and